Now we're going to talk a little bit more about polygons in general. Now we've already looked at polygons. We've looked at three-sided polygons, which are triangles, and we looked at four-sided polygons, which are quadrilaterals. So we talked about parallelograms and trapezoids, but now we're going to talk about just in general, what happens if you have more than four sides? What do we call those? And what are some properties of those things? Well, when we talk about a polygon, what we have are things that look like this right here. Notice that it has these sides and it's closed, and each side touches two other sides at a vertex like this, okay? So it's closed. So this is an example of a polygon. This is an example of a polygon. However, this is not a polygon. Notice it's not closed. You've got this opening here. This is not a polygon because you notice that it's this way. You take this side and it crosses over here like this. It crosses another side. Okay? That is not a polygon. When we talk about a polygon, we mean it's space in here. Okay? There's no crossing like this. Okay? Now, we classify these polygons. We have convex polygons, which are like this one, in contrast to concave polygons, which are like this one. Now, we're going to primarily study convex polygons. And the way you can think of that is if you go to any one side of a polygon and you want to get to another side of a polygon, if you only cross interior points of the polygon, we say that's a convex polygon. So if I'm right here and I want to get over here, the journey takes me just through the interior of the polygon. However, and that's true for this one over here in some cases. However, let's suppose I'm here and I want to get to here. Well, I cover this wasteland of stuff that's not in the polygon. That makes it a concave. We're going to study primarily convex polygons. Okay, now in the family of convex polygons, there are what we call regular polygons. A regular polygon has all the sides are of equal length and all the angles are of equal measure. So this right here is an example of a regular polygon. And so those are the two main classifications. We're going to talk about convex and regular polygons. Now, primarily, the names of the ones we're going to be studying, we've got triangles, quadrilaterals, pentagons, hexagons, and octagons. Of course, the pentagon has 5 sides, pente. The hexagon has 6 sides, and the octagon has 8 sides. Okay, and here's a picture of some more polygons right here. Some of them start to look just like circles. Okay, it's hard to tell the difference between those and a circle. Okay, now one of the things we're going to do is we're going to talk about the measures of the angles associated with a polygon. For example, notice this polygon right here. Or let's just look at these polygons down here. What we have is we have interior angles of these polygons. Okay? These interior angles right here. These are what we call interior angles. Now, we also have exterior angles, but we'll talk about that in just a second. So what I want to look at is the sum of the measures of interior angles of a convex polygon. Okay, remember convex is like this. And I want to look and see what happens when I add this angle to this angle to this angle to this angle. What is going to be that sum? And notice this is a 4-sided polygon. So what is the sum of the angles? Well, let's consider this polygon right here. Now notice it has 6 sides. 1, 2, 3, 4, 5, 6. And let's suppose that I just make a triangle out of each one of those sides. I have a center point right here, okay? And I just make a triangle. For each side, I make a triangle. Now, if I do that, notice what you would get. You would get 1, 2, 3, 4, 5, 6 triangles. Each of those triangles have a measure of 180 degrees. So if I just add those up, I would get 6 times 180. Okay? But wait a minute. I don't want these angles right here. These are not part of the interior angles up here. So what I want to do is I want to subtract off these angles. Well, if you notice, this angle plus this angle plus this angle plus this angle plus this angle, all of these add up to 360. So I'm going to take these triangles, 6 times 180, and subtract off the sum of the angles of the interior, of the center. So I take 6 times 180 minus 360, and dig this. I'm going to factor out the 180, and I get this, which is 720. So for the hexagon, this 6-sided figure, the sum of the angles is 720. Now, in general, what we're going to do is we're going to say you're going to take 180 times the number of sides minus 2. So for a triangle, that would be 180 times 3 minus 2, which would be 180. Okay. If you have a 4-sided, you would take 180 times 4 minus 2, see, and you would get 2 times 180. But that's how we use that formula. So let's take a moment and see how we would use this. We've got 4 sides here, okay? And what I want to know, well, what is the sum of those angles? So I take 180 times 4 minus 2 equals 360. Okay, so I take this angle plus this angle, add up all of these. That has to equal 360. This is 7, 8, 9, 10. 10x equals 360. That means that x equals 36. So that's one of the types of problems that we can solve. Now, if I want the measure, let's just use that information. The measure of an interior angle of a regular hexagon. Well, I know that a hexagon, okay, and we've already found this, is 720. Okay, 720. And I want to know, well, what is the measure of one of those angles? Now remember, this is a regular hexagon. All the angles are equal. All the interior angles are equal. It would be 720 divided by the number of angles. See? 1, 2, 3, 4, 5, 6. So I just take 720 divided by 6 and I get 120. So each one of those angles is 120. Now what I want to do is I want to talk about the sum of the measures of the exterior angles. And the way we get the exterior angle is we just extend a side. So see this side right here? I'm going to extend it. I'm going to take this side and extend it. This side, extend it. Extend it. And you see I'm extending all these sides. Now I could have went the other way. I could have said, well, let me go this way. Extend that side, extend this side, extend this side, and so forth. Okay. But I'm using these. So what I'm trying to do is say, well, what is the sum of those exterior angles? And I'm saying that it's 360 for a convex polygon. Okay, so if we add up all those angles, now you might say, well, how do you know that? Well, look at this. Let's take this angle right here, and I'm going to move this down here. Okay, now let me take this one, move it down here. Take this one, move it over here. Take this one. Now you see what's happening. I'm getting all of these angles, if I put them in the center, you can see I just get, I get a circle there, which is 360. So all of those angles would definitely add up to 360. Okay? So so we've got interior angles and exterior angles. Now, I want to talk about the areas of polygons. I'm going to go back to this six-sided polygon here, okay? And these are regular polygons, okay? The areas of regular. What I'm saying here only it only relates to the regular polygons. Now, if you think about it, I can make triangles, as I did before. Out of each side, I can make a triangle. So I get six triangles here for this one. And the area of this triangle right here and all of these is just going to be 1/2 base times the height. Now let's call the height this thing right here. I'll call that the apothem. Okay, the apothem. And the area of the triangle is going to be 1/2 the base, which is the side length, times the apothem. So in the case of a hexagon, it would be 1/2 x times a times 6, because I get the area of this, and then I say, oh, there's 6 of them. 1, 2, 3, 4, 5, 6. So it would be the area of one of the triangles times 6. Yeah, so that's the area. Now, let me play a little game here. Let me pull this 6 in here and pull the 1/2 out front. Now, notice I've got the 6s times a. Well, 6s, 1, 2, 3, 4, 5, 6. That's the perimeter. That's the distance around this thing. So in place of 6s, I could just put p, and then I have a here. See? Because the perimeter is 6s. So this right here is the area of the polygon. Okay? So if you know, so what you have to do is you have to figure out what the perimeter is. You just calculate that, and then you have to figure out what the apothem is. Okay, like this. Okay? And that is just going to be a matter of you looking at the triangle and then seeing if you can figure out. Now, what you'll be able to do is you'll be able to, you'll need some information to be able to figure out what this angle is. Well, you're going to have to get some information to calculate this A, this apothem. Okay, so sometimes that's the challenge. Okay, so if you know S and you know an angle, you can put that together. So let's suppose that we know that this is 60 degrees right here. Okay, and let's suppose that S is 10. Okay, then this over here would be 5. And what we have here is a 30, 60, 90 triangle. So we know the apothem. The apothem here is going to be 1/2 the hypotenuse times the square root of 3. So what is the hypotenuse? Well, look, this is 30 degrees here. The side opposite of the 30 degrees is 1/2 the hypotenuse. So the hypotenuse must be 10. So this must be 5 square roots of 3. See? It's 1/2 the hypotenuse times the square root of 3. Okay? So it's this times the square root of 3. And then you have the apothem. Yeah, so that's how you would find the area. Now, I want to transition out of that and show you a connection with the circle. Let's suppose that we have a polygon. Ignore this circle. We just have a polygon in here. And it happens to be inside this circle. Okay. And I know to calculate the area would be 1/2 the perimeter around times A. Now here's the deal. if we want to talk about the perimeter of these polygons, okay, if we want to talk about the perimeter here, imagine if we make the number of sides of the polygon more and more. Let's think about this up here. Here we have a 7-sided polygon. Here we have an 8-sided, 9, 10, 11, 12. Notice as I make these sides more and more, these polygons start to look more and more like circles. See? And by the time you get up to 100, you basically have a circle. So the perimeter of the polygon here is getting closer and closer to the perimeter of the circle. It's looking more and more like a circle. Well, a circle's perimeter, the circumference of a circle, is 2 pi times the radius. Now, where did we get that? Well, in a circle, let's just look at a circle. If you take the radius of a circle, and let me make it a different color here, okay? If you take the radius of a circle, and you take that length and put it along the arc of a circle, like that. Let's suppose this and this are the same length, okay? So I've got one radius length along that arc, and then I put another one. There's another one. So I've got 2 radius lengths. And then finally, I try to put another one, but it falls just short. In other words, I've got 1 radius length, 2 radius lengths, and not quite a third. Well, the number of radius lengths you would get there is pi, 3.14. You know, not exactly that, but approximately 3.14. That's how many radius lengths around a half of a circle. Now, so you put 3, 1, 2, 3. I said you don't quite get there. You do. You get 1, 2, 3, and a little more. Okay, I misspoke. You get 3.14, not just 3. A little more than 3. Now, if you want to go the whole circle, you would get 2 pi. So half a circle is 1 pi. A full circle is 2 pi. So what we have here is the circumference of a circle is 2 pi r. In other words, the perimeter. So as you make these sides smaller and smaller and increase the number of sides of a polygon, this 1/2 p times a becomes 1/2 2 pi r. And the apothem gets closer and closer to just the radius. So really what you have, these 2's cancel and you have pi r squared. So I'm just throwing that in there because we're going to make reference to that later, where we talk about the area of a circle and we're going to put polygons inside a circle and that sort of thing. But right now, we're just playing around with these angles of a polygon. And I wanted to make this connection with the circle here.